All right. Hello, everyone. Thank you for joining my session on working with calendars, dates, times, and time zones using the C++ standard library. My name is Marc Gregoire. I'm a software architect for Nikon Metrology based in Belgium, and I'm the author of a couple of books. The last one is the 5th edition of Professional C++, which has been updated at the beginning of this year to include all the C++20 features. I'll be talking about the following topics. I'll be talking about compile time rational numbers, durations, clocks, time points, dates, and time zones. Actually, only the last 5 of these are part of the so-called chrono library. The first one is not really part of the chrono library, but it's part of the ratio library. However, I will still briefly discuss this ratio library because not everyone knows how to use it, and we will need it during the discussion of durations. So I would like to go first through all the material that I have, and then I will answer questions at the end of the presentation. There are slide numbers in the lower right corner, which you can use as a reference in your question. All right, let's start with compile time rational numbers. They are defined in the ratio header, and they allow you to handle rational numbers at compile time. The numerator and denominator of a rational number, they are always compile time constants, and they are stored in a normalized representation. So we'll have a look at a couple of examples on the next slide. As I mentioned before, we will need these during the discussion of durations in the chrono library. Let's look at an example how to use these rational numbers at compile time. So since everything is happening at compile time, we are not using normal variables. Instead, we're using types. So in this first example here, I'm defining a type R1. I define an R1, which represents the rational number 1/60. Once you have defined this rational number, then you can use the num and then members of the rational number to retrieve the numerator and denominator. Then you can output them, and then you see that this R1 represents the rational number 1/60. Once more, it's all compile time constants. So if I would like to make a ratio with the numerator n and denominator d, but define these as non-constants, then you will get a compilation error because everything needs to be done at compile time. Still, it is possible to do arithmetic with these rational numbers. Again, everything is happening at compile time, so you cannot use the standard arithmetic operators. Instead, you need to use these special templates like ratio add, ratio subtract, multiply, and divide. Let's look at an example. Here I am defining 2 rational numbers, R1 and R2. R1 represents 1/60, R2 represents 1/30. And then I can add these two together using the ratio add template, which has a type member, which represents the resulting type of this addition. And we store it in the result. When we output the numerator and denominator of this result, you will see that we get 1/20. It's 1/20 because, as I mentioned before, a compile time rational number always stores its representation in a normalized way. Similarly, comparisons are also supported, but again, you cannot use the normal operators. For this, you need to use templates like ratio equal, ratio not equal, and so on. And these templates, they return a bool constant, and you can use the value member of the bool constant to retrieve the value of the comparison. So here I'm using the ratio less template to compare R2 with R1, and I'm storing this resulting bool constant in res. And then I can use the value member to retrieve the actual value of this comparison. The standard also defines a number of predefined SI type aliases. So we have things like atto, femto, and so on, all the way to beta and hexa. And actually, there are a couple of more. There is also support for yocto, zepto, zeta, and iota, but only if your compiler can represent their numerators and denominators as integral values. And I will give an example of using these predefined SI type aliases in the discussion of duration, and that is the next topic. So durations. What is a duration? A duration is an interval between 2 points in time, and it can be represented by the stud duration template from the chrono library. And basically, the stud duration class contains a tick, or a number of ticks, and a tick period, which is the time between two ticks, the number of seconds between two ticks. And this is represented as a compile time rational constant. So here you have the class template of the duration class template, and you see there are two template type parameters. We have rep, which is a type used to represent a tick, and this can be either an integral type or a floating point type. And we have a period, and that is the compile time rational constant to represent the tick period. Let's have a look at an example. Here I'm defining D1, and it is a duration with a tick period of 1 second. So I'm specifying ratio 1 here. And the number of ticks is stored as an integral value of type 1. 1 second is the default for the duration, so you can just omit it and write it more shortly like this. To define a duration where ticks are 1 minute, you just specify ratio 60. If you want a duration where ticks are a 60th of a second, you specify a ratio 1/60. And here we can use these predefined SI rational constants that I mentioned earlier. So now I'm defining D4, which is a duration in milliseconds. And we store it as an integral type of type long. What can we do with durations? So we can compare durations. We can compare one duration with another one. So here we have a D3, which is expressed in minutes, so ratio 60, and it represents 10 minutes. D4 is expressed in seconds, and it represents 14 seconds. Even though they are different kinds of durations, we can still compare them using the normal comparison operators like this. Durations also support arithmetic, and this can be done with the standard arithmetic operators. So here, for example, I'm incrementing D4, which was 14 seconds on the previous slide, so I'm incrementing that by 1, which results in 15 seconds. I can multiply it by 2, which results in 30 seconds. Now I can add two durations and store the result with a precision of minutes. So I'm adding D3 and D4 together. I'm stored in a D5, and I say one tick should be 1 minute. But here, of course, since adding D3 and D4 together, it can result in a non-integral value. So you have to make sure that you're using a floating point type here to represent the number of ticks. So I can also add the durations and store them as seconds. So here I'm doing the same addition, D3 plus D4, but this time I'm storing in a duration where a tick is a single second. And in this case, adding D3 and D4 together will always result in an integral amount of seconds. So here I can use long instead of double. And now the duration has a count method. So you can use count to retrieve the number of ticks of a specific duration. So here we are outputting the number of ticks of D3, D4, D5, D6, and then we see that we calculated that 10 minutes plus 30 seconds is 10.5 minutes or 630 seconds. Durations can be converted from one type to the other. Here I have a D7, which represents 30 seconds. So now I'm converting D7 to a duration where one tick is 1 minute. So D8 is represented with ratio 60 here as the period. And I'm using double to represent the number of ticks because I'm converting from seconds to minutes, which can result in a non-integral value, so you have to use a floating point type. If not, you will get a compilation error. So if instead of this line here, I would write this, which is exactly the same except for the type of storing the tick, then you will get a compilation error. If you still want to do this conversion from seconds to minutes and store it as an integral value, you can force this conversion using a duration cast. Of course, in that case, the result of D8 will be 0 and not 0.5. The standard defines a couple of predefined durations. So we have things like nanoseconds, microseconds, and so on. And since C++20, we also have days, weeks, years, and months. And I will show an example on one of the next slides of how to use these. Additionally, the standard defines a number of standard user-defined literals. So we have age, minutes, seconds, milliseconds, and so on. To use these user-defined or standard user-defined literals, you need one of these four using directives, so either stud or stud literals, stud chrono literals, or stud literals, chrono literals. Any of these will make these standard user-defined literals available to your code. Let's see how we can use them. Here I'm defining a duration D9, which represents 10 minutes, where each tick is 1 minute. And this can be written more shortly using one of these predefined durations as follows, or even more shorter using a standard user-defined literal and auto-type deduction as follows. These predefined durations can be used to construct a full timestamp. So here I'm defining a timestamp T, which represents a duration of 1 hour, 23 minutes, and 45 seconds. One thing to keep in mind, though, is that these predefined durations, they use integral types. So if I have 90s, which is 90 seconds, I cannot convert this to minutes because that will result in a non-integral value. So that's the downside of these predefined durations. If you still want to do this conversion of converting the 90 seconds to minutes, you will have to use the more verbose way, and you have to make a duration explicitly saying that a period is 60 seconds, and where every tick is stored as a double, and then you will get 1.5. The next topic is clocks. So the standard defines a number of clocks we have. First, we have a system clock, which is the wall clock time from the system-wide real-time clock. We have a steady clock, guaranteed to never goes backwards. So basically, it guarantees that its time point will never decrease. And that is not guaranteed for a system clock because the system clock can be adjusted at any point in time. And finally, we have a high-resolution clock. That's a clock with the shortest possible tick period for the platform that you're working on. On some platforms, it might be, or for some compilers, it might be that the high resolution clock is simply an alias for either the system clock or the steady clock. And C++20 adds a couple more clocks. So it adds an UTC clock, a TAI clock, a GPS clock, and a file clock, but I'm not going deeper in on these special types of clocks. What is important to remember is that every one of these clocks has a now method that can be used to retrieve the current time of that clock. Let's look at an example. So here I'm using the now member of the system clock to get the current time of the system clock, and I'm storing it in a time point called T point. Of course, you can use auto-type deduction to write this a little bit shorter. And then I'm using the toTime T member of a system clock to convert my time point into a time_T. And then I can use the local time function, which is defined in the CTime header. And I can use it to convert my time_T to a TM. Then finally, you can use the putTime.io manipulator over here to output my TM to the console. So this will output the local time of your system clock to the console. Clocks can be used to execute the time a piece of code takes. So To do this, you use the high resolution clock. First, you get the current time of the high resolution clock, then you execute the code that you want to benchmark. Of course, you have to make sure that the code you want to benchmark doesn't finish too quickly, because it needs to be measurable. And at the end of your code execution, you just retrieve the high resolution clock again, and you calculate the difference, and then you can output, or you can convert this difference, for example, into milliseconds. We are using, again, this SI predefined alias, and then you have the time it took to execute this gray piece of code. Next is time points. So a time point is represented by the time point class from the chrono library, and it's always associated with a clock that we just discussed in the previous couple of slides. And basically, a time point represents a point in time as a duration, and with relative to the epoch, and the epoch is the origin of the clock to which this time point is associated with. And time points, they also support arithmetic, but only arithmetic that makes sense. So in this table, you have TP, which is a time point, and D is a duration. So what I can do is I can add a time point and a duration together, the first column, or I can subtract a duration from a time point, or subtract a time point from another time point. Those are the arithmetic operations that are supported. Here's an example. I'm creating a time point representing the epoch of the associated clock. I add 10 minutes to it, and then I store the duration between the epoch and the time point as a duration D1. And then I convert this into seconds, and this gives me the output of this piece of code is 600 seconds. Remember here, I'm just specifying double for the duration because seconds is the default for a duration. Time points can be converted as well. So we have implicit conversions. For example, if you want to convert seconds to milliseconds, that can be done implicitly. So we have TP seconds, which is 42 seconds. It can be implicitly converted to milliseconds as follows. And if you output this, then you will see that you get 42,000 milliseconds as expected. If the implicit conversion can result in a loss of data, then you will need an explicit conversion using time point cast, similar as using duration cast during the discussion of duration. So here I start with 42,016 milliseconds, and I'm explicitly converting this to seconds using this time point cast here, or of course shorter using auto time deduction. And if I convert these seconds back to milliseconds, you see that we arrive at 42,000 milliseconds because you lose precision when you move from milliseconds to seconds. Next topic is dates. So C++20 added support for working with dates. At the moment, only the Gregorian calendar is supported. With the C++20 standards, there are lots of classes that allow you to work with dates or part of a date. So you can use the class year to represent a specific year or a month or a day. There is a specific class to represent the last day of a week. You have something like Monday, which represents a specific day in a specific month, or year Monday, which represents a specific day in a specific month of a specific year. And we'll get clear how to use this with a couple of examples. So let's look at the easiest first. So you can construct a specific year, 2021, using two ways. You can either just use a simple constructor call, or you can use a user-defined or a standard user-defined literal y as follows. You can construct a month, again, in two ways. You can call a simple constructor or use one of the predefined months that are available in the standard. Finally, you can construct a day, again, with a constructor or with a standard user-defined literal d, as in this last line of code. You can create a full day or a full date. So here I'm creating a year Monday, which represents today, 27th of October 2021. You can use auto-type deduction to make this shorter. You can also write the date in a different order. So you can first say the day, then the month, and then the year. Here I'm creating a year Monday for the 4th Wednesday of October, and the syntax is that you specify you want a Wednesday, you want the 4th one of October 2021. You can also use these classes to specify parts of a date. So here I'm defining oct27, which represents the 27th of October, but of an as of yet unspecified year. So you don't see any year mentioned here. And then I could construct a full day for today, October 27, 2021, by specifying the year 2021 and using my oct27, which we defined on the previous line. Another example, I can construct a month day last for the last day of October of an unspecified year as follows, and then use this to construct a full date like 2021, and then I say last day of an October. So this represents the last day of October 2021. And the last example is this one, which represents the last Monday of October 2021. C++20 added a couple of new type aliases. So it added system time, systime, which is a type alias for a time point of a system clock with a certain duration. And 2 additional type aliases are defined to represent a system time with a precision of seconds, first one, and a precision of days. So these are all serial types. So they are represented by a single number, the time since the epoch of the associated clock. On the other hand, you have the field-based types like year, month, day, which we discussed on the previous slides. And when you're doing a lot of arithmetic operations with dates, it's often more performant to use one of these serial-based types instead of the field-based types. Let's have a look at how you can use these. Here I'm using the now member of the system clock to get the current time, and I'm using floor to truncate the current time to a precision of days, and I'm storing that in today. You can convert a year, month, day to a time point. So here 2020, June 22 represents a year, month, day, and I'm converting this to a time point, storing it in T1. The opposite conversion, converting a time point to a year, month, day, can be done with one of its constructors. So here I'm just constructing a year, month, day and pass it a time point T1, which I truncate to a precision of days. Of course, you can also just get the current system clock time, truncate it to a number of days, and use it to construct your year, month, day. You can construct a full date, including a timestamp. So here we're specifying the date as a sys days, and then we say it should be at 9 o'clock, 35 minutes in the morning. You can do arithmetic with this, so you can take this full timestamp and let's say we add 5 days to it. Date supports streaming, so you can just output them to a stream. And if we look at this, then we see that D2 is indeed 22nd of June 2020, and D3 is 27th of June, which is 5 days later, so the result of this addition. But you have to be careful with this. So some arithmetic with dates might give seemingly unexpected results. So let's have a look at an example. Here I have a D2, the same as before. And now I'm trying to add 1 year to it. The output might look unexpected. So if you look at the date part, you will see that indeed 1 year has been added. So it's 22nd of June 2021. However, the timestamp looks quite unexpected. And the issue here is that we are working with serial types. So this sys days is a time point, and a time point is a serial type. And so it's the date is just represented by a single number. And the standard mandates that if you add 1 year to a serial type, then you must add 1 average year to keep into account leap years. So when you add 1 year to this date, you're not adding this 31 million seconds, which is 365 days multiplied by the number of seconds in a day. No, this statement actually adds this number of seconds because it's using this more complicated formula to keep leap years into account. If you don't want this behavior from the previous slide, then of course you can use field-based arithmetic. So again, we have our D2 defined as before, and we first truncate D2 to a number of days, and then we calculate the remaining number of seconds by subtracting D2 days from D2. We can convert the number of days to a year, 1 day. Then you can easily add 1 year to this field-based representation, and then the final result can be retrieved by converting my incremented year, 1 day to a sys day again and adding the seconds that we calculated over here. If you output this, then indeed you see that the timestamp is untouched. And the final part is time zones, which is also new in C++20. So to be able to work with time zones, you need a database that includes all the time zones in the world, including things like daylight saving time descriptions. And you can get access to this time zone database using get_tzDB. If you then iterate over every time zone in the database, you can output its name, and then you know which time zones your system supports. You can retrieve a specific time zone based on a name. For example, here we get the Brussels time zone or the GMT time zone. And you can also just query your current system for the currently active time zone. And then these time zones can be used to convert times. Here I'm getting the system clock, the current system clock time, and I'm converting it to a GMT time. Another example, here I'm constructing a UTC time, like we did on the previous slides. And I can convert this UTC time to a Brussels time using the Brussels time zone that we retrieved over here. And then you can also, of course, construct a specific time in a specific time zone. As an example, I'm retrieving the time zone for Brussels, and then I create a so-called zoned time in hours. And the first parameter to this constructor is the time zone that you want to use, and then you specify the time that you want to represent in that specific time zone. And of course, zone times can be converted between different time zones. So here I'm converting my Brussels time to the time in New York. And that's it, what I wanted to speak about today. If there are any questions, I think we have like 2 minutes. So the first one, you showed 9 hours for 9 a.m. and I believe 21 hours will be 9 p.m. Is there an equivalent of a.m. p.m. in chrono? That is something like 9 hours underscore a.m. No, so I think you are talking about these standard user-defined literals. They don't know the concept about AM or PM. So where is it? Anyway, the H standard user-defined literal does not know the context about AM and PM. The next question, it jumped around. If you add a year to February 29 on a leap year, say February 29, 2020, do you get February 28 or March 1? That is a good question. So it depends on which kind of arithmetic you're using. If you're working with a serial-based representation, then it will add that 31 million seconds to it, and then it will just calculate onto which day it will be. So it will most likely be March the 1st. If you use a field-based arithmetic and you add 1 year to that, then I'm actually not sure what will happen, because it will represent an invalid date. So that I will have to look up what happens there. I think we're running out. It's 6:05. So yeah, if there are any more questions, you can always find me on Discord and ask your question over there.